Thank you. I'm going to try my mic here and see if I can make this work. Does that sound okay? Everybody here all right? Okay. I am going to talk tonight about a number of things. Urban density, one of the big issues that affects conversations or influences conversations about biodiversity. I'm going to talk about ecological urban design, not just planning, but design, which I think of as slightly different. And I'll be talking about strategies that have been built, some unbuilt, in cities in different parts of the United States and in Europe. And I'm going to end my talk by talking about climate change and what relationship that may have to the work that's been done so far, at least what we think can be done in cities in relation to biodiversity. So I hope that that will be a comprehensible range of subjects. I always feel like I've come a long way to come home when I come back and speak at Harvard. I was born in Dorchester and grew up in Worcester, so it is indeed a circuitous route. This is an image on the title screen of a newborn harbor seal pup that was coming up onto a beach in West Seattle just last week. This is the season when seal pups come up onto the beach. Their mothers are fishing, and they drop the kids off, who crawl up onto the beach in quite urban settings, literally pull themselves up the concrete stairs of urban waterfront onto areas near this concrete seawall and wait there for the day, and then go back down to the pullouts when mom comes back from eating salmon that are coming out of the mouths of rivers, or going back to the mouths of rivers this time of year there. So it's an interesting pattern to see, and my 10 years in Seattle really reassured me in a way that it is possible for urban development to coexist with biodiversity. It's the kind of place, if you haven't been there, where like Vancouver, British Columbia, or Alaska, you can be in an urban context and see whales swimming off the shore of an urban park, see eagles hunting for salmon, again in an urban park, and those things are rare opportunities in much of the world now. So it's also useful for me to remember that, and remind people that there are different goals for biodiversity in different parts of the world, and people have different senses of what an achievement is in an urban area, depending on the current context and the historical context of what's happened to biodiversity in those areas, or what the original biodiversity was in terms of numbers of species or kinds of animals and plants. As a former geologist, I have to always point out that it does seem striking to me that cities are a new phenomenon. 7,000 years is a drop in the bucket when you look at the history of the Earth. And geologists are prone to these sorts of analogies, so I'm showing my stripes right away. Cities are, I think, genuinely an emergent phenomenon in a dynamic system. They would have been difficult to predict if you had visited the Earth 25,000 years ago and seen the human species in its way of living at that time, that we would emerge urban dwellers and then spread that pattern over so much of the globe to the point where by 2030 the United Nations expects 60% of the human population to live in cities. So it's, I think, a very interesting thing, and it's no wonder when you look at it in a geologic timescale that it's been difficult for us to figure out how to work cities, how to manage them, because we're just still getting used to them. They are new on the scene. I want to talk a little bit about the history of thinking about urban ecology and urban design, not too much, mostly just about some data issues on this question of density. The first urban plan that really addressed what I would call an ecological issue is John Claudius Loudon's 1829 plan for London, where he proposed breathing spaces, the necessity of what he called breathing spaces for human beings in a city. Every half mile there should be a green belt that allows people to get fresh air. And this is the city of the industrial age, where the air was everything but fresh, and people were concerned about diseases like tuberculosis that were killing a lot of people in urban areas. In fact, a historian friend of mine, Sam Bass-Warner, tells me that cities couldn't actually reproduce internally by their own birth rate until after 1850. They grew by in-migration. So it's interesting to think about a city that was, in a sense, a sink for the human population, and that explains a lot about why people were so concerned to try to figure out how human health and cities could coexist. This is, of course, a Google Earth image of the Boston Fenway, and this is, I think, one of the most important and original American contributions to urbanism in the category of looking at density, human health, and ecological function. Most of us don't realize that in Olmsted's original plan, his design for this area to change what was then essentially a piece of a tidal estuary when the Charles was an estuary and still had about a 9-foot tidal difference every day. He was taking an area that was full of raw sewage, and as the tide came up during the day, that raw sewage would be stranded on the banks of a park. And then, of course, the water would go down, leaving it there. And women and children who were at the park during the day, caregivers, would be exposed to diseases through the exposure to human waste. This is before germ theory, so people were using the kind of miasma approach to explain this. But Olmsted changed that condition by putting a tide gate on the end of the muddy river and making that freshwater only, which today we'd say, well, that's a pretty major change for an ecosystem that you wouldn't necessarily want to do. But at that time, he was trying to safeguard human health and still allow that system to carry human waste and to carry stormwater throughout the city. So it was the first example that I'm aware of a park system, the Emerald Necklace, that did a function beyond recreation and beyond something that was associated with air quality. This is the first example, I think, of a park system that offered water conveyance, that safeguarded drinking water quality, and that safeguarded human health in terms of sewage water. So it's a very important example, and I think the most significant American contribution to urbanism. This is Venice, very different city. And you can see, looking at it, why when designers meet designers, and it's American designers talking to European designers talk about the European city with a certain reverence about what density means. They're talking about a very dense place that has typically very few open spaces of any kind, except paved piazzas in the case of the Italian landscapes, or marketplaces in the case of Northern European landscapes. This is Stockholm, often called the Venice of the North, and you can see many 1,000 miles away how similar in some ways the density is on this island to that island. People built out every square inch, and the roads were what was left over from the division of the land into parcels. The roads were often winding and quite narrow, and Europeans are in many cases mystified at the American development of things like Commonwealth Avenue here in Boston, where in many cases they think that the density of American cities has gone too low. I don't think in Boston that's the case, and there are many examples of the European Boulevard, which really is a 17th and 18th century development in Europe also, part of the Baroque period. But the connection between this boulevard and the linear park system and the large patches of parks in the Emerald Necklace is really the American version of this functional system that created, in a sense, a lower density overall. This is a much older version of a water system. It's not a park, but it's a qanat. It's the water that comes out of an irrigation channel that was dug from the mountains to the agricultural plains in countries like Iran, the previous version of Iran. This is 1,000 years old, these kinds of channels. It's passing by a walled garden on the sides. Looks a lot like that medieval street in Italy. This is the city of Tehran, the modern city of Tehran, a city now of, I think, 13 million people. And it's still divided into districts based on the irrigation channels that existed when the city was first developed. So you see a legacy in the urban pattern of the water conveyance system in the way that districts evolved. And you can still see that legacy in the street. This is a street scene in Tehran showing stormwater in a channel that probably was related to one of these agricultural systems in the earliest years of the city, when it was a village with agriculture around it. So it's kind of amazing to think about the way that these systems persist as cities develop, whether they're dense, or whether dense in the European sense or the Middle Eastern sense, or whether they're dense in the American sense. There's also an argument for energy savings in density. You'll notice in this chart by Peter Newman from the 1980s that all American cities are up here in this zone. This vertical axis shows the transportation-related energy consumption in that city, and the horizontal axis shows urban density in individuals per hectare, I think. And all the American cities are here, and European cities are here, and Asian cities are even further. So in terms of the advantages of density, in terms of energy, there are clear advantages. But that also has to do with investments in transportation, public transportation, and other kinds of savings, besides just the spatial qualities of density. urban ecology, in many ways, first developed in Berlin. And the argument about that, why that happened in Berlin, is that this man, Herbert Sukop, an ecologist who was studying at the university there, when he became a researcher, a faculty member, it was at the time when the wall had just gone up. And he couldn't exactly wander outside that wall. If any of you visited Berlin when the wall was up, you know that it was very difficult. You had to only under certain circumstances go to the east. Typically, you lived your entire life inside the wall. And he began to study wetlands and forests inside the walled area of Berlin and discovered a surprising diversity. At the time when the bias was that there wasn't much diversity in cities, Sukop showed with data that there actually was a surprising level of diversity, particularly of plants, in urban areas. He developed these kinds of diagrams to explain that the city has different zones. It's not just the most visually striking, densest part of the city. It's the rest of the city and its water table that's influenced by urbanization and can generate a fair amount of diversity within the heterogeneity of an urban landscape. His colleagues mapped things like the dates of flowering of linden trees in different parts of Berlin, and the detail with which they studied the relationship between microclimate and plant flowering, for example, have been models for the way we now look at the initiation of climate change, collect data about how plants are responding to climate change. And you can see that there's a fair amount of diversity in the city's microclimates, and that was another explanation Sukop gave for why the city is so prone to high diversity. In his mind, the data seemed to show that it was related to a variety of microclimates, that kind of heterogeneity, as well as the heterogeneity of different soil types and other areas. This is a very old plan of Rome, and I only show it because I want to explain, I think, why urban design got so off the track in the way that it approached things. This is Noli's plan of Rome, and it shows buildings in black and the rest of the landscape with a kind of funny aerial view, side view, aerial view of plants and garden areas. It also shows, this is a church, it shows that it's white because it's public space. The church is considered public space. And these are the columns that support the center of the structure. This was a plan originally developed for purposes of taxation, as I understand it. And that was a very specific reason to develop this plan. It became the basis for how urban designers thought about what became a kind of ideal urban city, the Italian version of urbanism. And people like Colin Rowe at Cornell and other places began using figure ground images based on the Noli plan to talk about cities. In fact, the Noli plan was actually striking, and it was the first plan to be oriented with north up, the first urban plan oriented with north up. In fact, the word orient, if you think about it, comes from the common tradition before Noli of orienting everything east up. That's where the phrase to orient, the verb to orient, comes from. So we think about these figure ground drawings as, at least architects thought about these figure ground drawings as the basis for thinking about structure in cities. Now you notice in this one there are no plants, and the whole thing has been broken down to just masses of buildings and then some definition of paved spaces and other spaces, but there's no definition of plants or gardens in this. So it's a really stripped down version of the Noli plan that became the standard that was used in urban design. I think that was unfortunate because it left out a lot of information. The tools we use to visualize are so important to what we can and can't manipulate as we make plans and designs that was, I think, a crucially difficult time for talking about anything other than the masses of buildings and the layout of roadways in cities. And that was really, reached its height in the 1950s. And then persists still today, but from people who were trained at that time who operate in urban design using only that information and believe that it's the most crucial information to have. This is a study, a figure from a study that was done recently in the city of Halle in the former East Germany, and not too far from Leipzig. Data from plots that were measured in the city. This is a study of plant diversity in an urban area and an agricultural area of Eastern Germany. And it shows that in the different plots that they analyzed, the number of native species, which is the gray here, was actually higher in the urban area than in the agricultural area. And Europeans use the term archaeophyte for plants that were new to the region, but new meaning pre-1500 AD. And neophytes for plants that are new meaning post-1500 AD. And natives for plants that were older than all of those that they think are actually endemic. So you can see here that the urban area actually not only has more species total, but it actually has more native species. That's a result that's been found in a number of places around the world. It's interesting to see it here in a situation where it's a very intensive agriculture outside the city. If you visited Eastern Europe when it was under the Soviet bloc, that was a very, fence post to fence post kind of agriculture, fence line to fence line. So it's not as if there was a lot of habitat left over. So it may not be the most convincing example. Here's Phoenix. In the Phoenix area, a study was done recently by a group that's at the Urban Long-Term Ecological Research Station there, and these red dots show the number of genera, not species, in the different areas of the city where they're showing agriculture in green, purple is the urban, and yellow is the desert. And you can see in this map that there's a lot of genera. There are a lot of genera in the urban area and in the desert, but many fewer genera in the agricultural lands. They did a number of studies to demonstrate that the urban area actually had quite a bit of diversity. They wouldn't have probably argued that it was more native plants. In fact, it didn't have more native plants than the desert area had in North American context. But it had more plants total than the desert area had. So it has a higher diversity. When you think about diversity as just richness, just number of species, as opposed to native species. It was also interesting that they've been looking in these long-term ecological research stations, both in Phoenix and in Baltimore, at the relationships between social patterns like socioeconomic level and biological patterns like plant diversity. And they found that higher plant diversity was correlated with higher family income. And it seems, therefore, that you might draw the conclusion that a lot of people who have, they call it the luxury effect. If you have a little more money, you spend it on special plants. And if you have less money, you spend it on basic plants, the same plants everybody else has. That's their hypothesis from that study. And they also learned that sites that were previously agricultural had fewer than half as many total species as sites in the urban area that were not previously agricultural. So agriculture seems to wipe out some of the diversity in genera, and then urbanization afterwards is depauperate for that reason, if it comes after agriculture. So it's very interesting as these data come out, how to think about urban areas in different contexts. This is a different kind of problem with an invasive plant in urban areas in Pakistan, where this Parthenium species has been taking over a lot of dryish primary succession areas and is actually not palatable to grazing animals and replaces medicinal herbs that people rely on in low-income urban areas like Pakistan has, in Islamabad or Lahore. And those places are changing a lot because of the invasion of the species. So there are dynamics that are crucial, that are happening in poor parts of the world that are very important and large scale, in addition to what's happening in North America or Europe. This study from Europe also showed, this one is from the United Kingdom, that as people have lower incomes, they also feed birds less. So this one was a study of people are feeding birds. You do that if you have more money, not so much if you have less money. So it's interesting to think about what social education or information we might provide to people at different income levels about what the effects are of bird feeding. This is one of the other charts from that study, a recent study from 2008, showing that feeder density, mean feeding households per square kilometer versus avian species richness doesn't have much of a relationship. That just shows there's not much of a prediction you can make based on feeder density about the diversity of birds, species richness, the number of species of birds. But the feeder density does have a relationship with the mean avian density, or the abundance of birds, the total abundance of all species. So you can see here the food subsidy effect that we create in urban areas. I'll talk more about that with other species later, but from intentional feeding in this case. And here also there are relationships shown in the graphs between the proportion of people feeding and the mean number of species, and the proportion feeding and the total abundance of birds. So you see the effect that humans have on the populations of birds. It's not a huge surprise, but it's important to have these data to be able to understand better what the implications are of the way people behave in relation to other species. So I want to talk a little about ecological urban design. I'll talk about some more data, some more studies as I go, but I wanted to try to emphasize today some of the issues that come up when you try to take on ecological functions as part of actual design and planning projects. I use this kind of cheat sheet, a heuristic for myself and my students to think about design strategies that actually explicitly take time into account. I'll just mention a couple of them. This one is the palimpsest. It's a common design term, relatively common. It just means that something from the past was continued into the future, literally. The actual foundation of a house was used as the actual foundation for something else in a new design. So it's a very literal continuation of some structure into the future. The idea of the garden is one where you reveal human maintenance as part of a design. It's not hidden. It's not meant to look like no human maintenance occurs. It's actually clear that human maintenance happens, like when tomatoes are harvested in an allotment garden. You see that, and there might even be a ritual associated with it, a party. So there's a revelation of human involvement in the landscape. The scaffold is one. I use a design that a classmate of mine did 20 years ago that was one of the first designs that I ever saw that used a simple structure where our studio was being asked to design an island off the coast of Dorchester, off the shoreline in Dorchester. And she proposed putting in a concrete system of linear pieces that in plan looked like a fish skeleton. And the idea was, she knew, that in the shallow waters of that area, sediment would accrete and salt marsh plants would probably also arrive on that sediment, and a kind of fleshing out would occur of this structure over time, not in the symmetrical and literal shape of a fish, but in some kind of halo around the structure itself that she would have inserted. This idea of inserting a structure and letting things accrete to it is a relatively new idea, where the designer doesn't make the finished form. The designer inserts something, and the form is created by processes that are non-human processes over time. And Jim Corner at the University of Pennsylvania has called that a scaffold. Ann Spurn called it a catalytic framework. But it's become a very important idea in how we think about design now, and not trying to make the finished form, trying to make something that either appears in this case or disappears. In this case, in Seattle, I was working on helping people with private land provide what geologists call gravel recruitment to salmon streams. Salmon streams in urban area often lack gravel, which is a critical component of spawning in a substrate. Salmon need to spawn in gravel of a certain texture. And rather than walk along the stream and say to people, you know, I need to take away part of your yard, which doesn't go very far. Imagine that conversation. Knock on someone's door. I'll be taking away, 300, 500 square feet of your backyard. That's not going to happen. People instead were asked if they would like to have a gravel terrace or a patio in their backyard on the stream that they could use, and when a flood came along, it would be eroded. It would go downstream, as it should, to supply substrate for salmon habitat, and the city would replace it. So it seemed like a win-win. The city was otherwise trying to look for semi-natural areas to dump truckloads of gravel in, but you can't just dump a big pile of gravel in the middle of a stream, because that affects the way that fish would move through that stream and isn't the right way to distribute the gravel. So that's an idea that I call a candle. I'm looking for a better word, if anyone has any suggestions. But the idea is that you design something that's meant to go away, and a candle, when it's working, goes away. So this is another different idea in design. And I'm showing these at the site scale, but they could be used at any scale for different kinds of things I'll talk about as we go on this evening. The last one I wanted to mention is an idea from older cities, very old cities, the first cities, called a temenos. It's a sacred area in a city that actually was the grounds of the temple. This is the temenos in the city of Ur. The city of Ur is one of the first cities of Mesopotamia. You can see in this particular example, it's a walled city on a mound with a temple in the center, a harbor, other features, some workers' housing. In these older cities, both in Ur and in Harappa and Mohenjo-Daro, these are cities that are now 5,000, 4,000, 5,000 years old. The compass directions were important to orientation, and there was an idea of space you couldn't go into. This is an idea that should be brought back. There should be places that are sacred places where people don't go. It's turned out in some studies of particularly East German surface mining that diversity increases where humans and dogs don't go. So how can we make this sexy for people? How can we make this interesting for people? Alan Sonfus did it in Manhattan. He took a piece of a block in Manhattan, it's called Time Landscape, back in the late 60s, early 70s, and he made that block as an art project inaccessible to people. And you just look at it from outside the fence. Piece of Manhattan, completely separate from human activity, just to look at, just to know it's there. The question, I think, is how do we design the edges of these places in urban areas at multiple scales, in individual gardens, in public parks, in larger regional parks. This one is an example from Lille in France. It's the Parc Henri Matisse, and it was designed by Gilles Clement about 15 years ago. And it includes a 7-meter, or about 21-foot high concrete plinth, which is 2,500 square meters. It's pretty large, and no one can get up in it. The idea is that it's for other species, not for humans. And it's a place you go, you see it there, and you know that it's there for other species, but no one goes in. No one goes up. I think that's a worthwhile component to reintroduce in various ways, as islands, as pieces of parks, as parts of systems, to make sure that we incorporate that as a part of our both kind of spiritual and practical understanding of sharing the world that we live in. This is an osprey, and I want to talk for a moment about cultural symbols. This is an important bird in the Pacific Northwest and in many parts of the United States. It happens to be catching 2 fish in that picture. This is a green roof proposed for Seahawks Stadium by one of my students in Seattle in a studio. And the student proposed seahawk nests, osprey nests on Seahawks Stadium, which seems like a no-brainer. But people have not done that, made that literal connection between the actual Seahawk and the mascot of a professional football team. But there's no reason why they can't do that. So I think we need to build on people's current expectations of symbols in ways that generate actual biodiversity. It's a big opportunity. Now, one of the problems of urban design, ecological urban design in particular, has been that we mistake structure for function. People have been putting structures in streams trying to improve salmon habitat. They've been putting bird habitat in place, trying to make sure that the shrubs or the trees are there, without thinking about what the community interactions are for that species. This is a very interesting topic and one that we need to know a lot more about to be able to do well. This is an American crow and a bluebird. The crow is a nest predator. It's a known nest predator, and it was checking out the babies in the bluebird box, and the father was mobbing or harassing the crow while it sat there, eventually chased it off. But many birds are not so lucky to have such an aggressive father who protects them so well. And the Pacific slope flycatcher is a bird in the Northwest which has suffered quite a bit from nest predation by crows. Crow populations are growing. Crow populations in King County, Washington, which is the county around Seattle, have been growing steadily since the 1960s. The white is the human population, the black is the crow population. You can see that the crows have a little bit of a lag, but they follow pretty quickly. And the best predictor of crow population density is the density of dumpsters that contain food, or outdoor cafes like Starbucks. So we see an enormous subsidy of food. I talked about food subsidies in the first section of this talk. We see the effects of the food subsidy in the crow population, and therefore the immense predator pressure that affects songbirds. So it's not a build it and they will come situation anymore for the songbird. It's a question of how to deal with a predator pressure which is invisible unless you know the data. One of my students in Seattle proposed using a berm. This is a model shown as a kind of mock-up, a berm of wire mesh. And his idea was that this could be made quite beautiful. It could be done with enamel and colors. It could be a public art project. But it would be installed during the breeding season between April and June in parks as a public art project. But it would cover shrubs and large ferns that are nesting habitat for songbirds, breeding habitat. And it would keep out larger birds. It would also keep out possums, cats, and squirrels, who are also nest predators. And not snakes, but luckily the snake is not a huge factor for a lot of songbirds. It is a factor, but not a huge one. So some kind of exclosure, which we use all the time in ecology to do experiments, might be an appropriate thing to introduce in urban environments, where it's not a permanent thing like the temenos, but it's something which allows temporary separation in time between predators and prey. And the small birds, of course, would be able to get in and out of the mesh, but the large birds not. It might also be used on green roofs as a way to promote songbird use of those new habitats in urban areas. There's another example of a bird that's interesting for conservation reasons, the ovenbird. When I looked at a competition for, well, I should say a little more the ovenbird first. The ovenbird's a ground nesting species. And actually it's pretty smart. So it'll avoid forest areas with high chipmunk densities because it knows what's going to happen. That is a train wreck for the ovenbird. So it doesn't nest in those areas. It does nest in a lot of woodlands and interior woodlands in North America, especially the northeast US and Canada. There was a competition for a park in Toronto, which is classic ovenbird habitat. And there are 5 finalists. There are 4 schemes shown here. And what I did was use a figure ground analysis, but it's an ecological figure ground analysis, where the black shows woody plants, shrubs and trees, the gray shows unmown grasses, and everything else is white. Because from an animal's perspective, this is what matters. So if we map the world through these kinds of tools, we can actually see very quickly what the landscape ecological value might be of the different proposals. This one by Bernard Schumy's team shows a large unmown grass area. He called it the cup of the wild, juxtaposed with what was actually a very active area here and a forested area, and obviously wins if the ovenbird was on the jury. This is a good one if the coyote is on the jury or some other species that moves through grassland areas, and this one is pretty lousy overall. Guess which one won? This one won. So the Kohlhaas scheme, which was supposed to be a series of patches that were had infinite variety and were very interesting, actually from the ecological perspective are pretty similar across the whole set of patches. We know a lot about patches and connectivity through the work of ecologists like Michael Dyett. This paper by Crooks and Dyett from 10 years ago now shows the relationship between coyotes, domestic cats, and native birds in chaparral fragments around the San Diego area. Now we're in Southern California. And it shows that the fragment of chaparral, if it's larger, that has a benefit to see more coyote in a larger fragment. That's what the plus sign means. If there are more coyote, there are fewer domestic cats. If it's just a larger patch, there are fewer domestic cats. If it's a larger patch, there are more native birds, wild birds. If there are fragments that are smaller, it's the opposite. You would see fewer coyote, more and fewer native birds. Fragment age was also a significant variable, the time since it was isolated, and it had a negative impact on native birds. So the longer the time since it was isolated, the fewer native birds you would find. And the hypothesis that they demonstrated some support for in this study was that having some larger patches that are better connected to each other for coyote movement would keep the domestic cat population down because the coyotes are eating the cats. And the cats would then be unable to eat the native birds. So your coyote is your friend. Unless you're a cat lover, the coyote is your friend in terms of native habitat species conservation. Coyotes are getting pretty clever. This is a coyote taking the light rail in Portland, Oregon 3 weeks ago. This is just 3 weeks ago. Pretty sneaky, pretty clever. When I first moved to Seattle, the paper showed a photograph of a coyote in an elevator. And it turned out the coyote had come down a downtown street in Seattle, walked into the federal building when it opened, walked through a revolving door into the federal. I don't even know how to use a revolving door. Walked to the lobby through a revolving door and into an elevator in the federal building at 7 o'clock in the morning. And it turned out that the Forest Service headquarters was in that building. And so we all assumed that the coyote had gone in to complain. But it was picked up by the animal control people, and it did not get a chance to say whatever it was that it had to say. So maybe this is it now on the subway, on the light rail in Portland. Animals change their behavior to, I don't want to say adapt, because that has specific ecological meaning, but they change their behavior in new contexts. And we have seen coyotes changing their behavior, also in slightly scary ways, where there are more interactions between coyotes and toddlers now than there used to be. Rhode Island has had a few cases of toddlers attacked by coyotes, where we thought that was all a kind of California problem with cougars. If coyotes ever started to do that more often, we'd have a real problem because they're all over, including in the subway, so the light rail, so we have to watch out. This slide is about, I'm trying to prompt myself to think, to tell you about ecomimicry. This is a slide of the Pacific Northwest coniferous forest, the coniferous rainforest before development, an example of what Seattle would have looked like, or Portland, Seattle in particular. And it shows you get a sense of wetness right away. And the forest actually could retain in the vegetation of the conifers and in the duff layer on the forest floor 11 centimeters of water across the entire surface. That's a lot of water. It's what, 7 inches of water, and that's a lot for it to hold. And the trick now in cities is we're trying to figure out how to mimic the ecological properties of the pre-development landscape. Particularly, there's been a focus on hydrology for lots of good reasons related to marine and aquatic biodiversity. Unfortunately, we can't yet figure out how to mimic providing spotted owl habitat in downtown Seattle, but we can talk about hydrology, and there have been a fair number of successful urban experiments constructed by the city in both Seattle and Portland, which are performing well. They were modeled, they were built for monitoring, and they have been monitored. So now we have data about new urban experiments that are really, really useful when you're making an argument about why cities should do things like this. This happens to be sockeye salmon, which is not the threatened species, but gives you a sense of the kind of substrate that salmon live in. And these are big fish. The typical urban storm generates a lot of urban runoff. This is a flooded ditch in a typical big storm in Seattle, not the usual drizzle. And what happens is that salmon young, their eggs and young, this is a magnified image, this is probably a half-inch diameter piece of gravel. These are very small eggs and fish. When they first hatch, they are flushed out. In fact, it's called fish flushing, out of the stream system by these large, flashy storm events. So we try to change the way the urban water system works. This is an image I love to use because it shows the direct interaction between urban infrastructure and an organism. This is actually the Chinook salmon, and the one that's been listed as threatened. This is a state highway outside Seattle, and a river has flooded over here, and has flooded this field, and the salmon have come into this sort of lake in the field, and they're all here along the edge. These are 3-foot-long fish, 2.5 to 3 foot long fish, waiting to cross, and when a car goes by, it generates a wake, and the fish thinks that's a signal of what's upstream. So they wait to cross, and then when the wake comes, they go. And people are actually getting out of their cars and trying to help these animals trying to pick up a fish that's basically got its skin falling off because it's the end of its life cycle. It's going up this stream to die, and help it get across the street. So there are jokes now about why the salmon crossed the road since this photograph was. We don't really know the answer, except we know it has something to do with urban flooding and water management. I want to point out a pitfall about statistical scientific studies in relation to urban design with the next 2 slides. This one shows 2 watersheds in the Seattle region. This is the city of Seattle, where red and pink are the most paved areas. Blue is kind of an intermediate suburban trees and paving, and green is the most unpaved, the most vegetated zone. These 2 watersheds are just an example. We have done many studies now around the country, and this again is sort of a dummy data slide, that show a relationship between an index called the benthic index of biotic integrity, which is a very complicated way of saying the diversity of macroinvertebrates, of larval insects in the stream. Now these are what fish eat, so they matter a lot to fish populations because they're the food source. In relation to another variable, which is total impervious area, total paved area as a percentage of land area in the watershed. Many, many studies have found this kind of wedge-shaped pattern in the data where there's a threshold at about 10 or 12% impervious where no stream sample exceeds the medium quality in this index of biotic integrity. So people had a kind of freak out and they said, oh my gosh, we can't spend any more money on cities in terms of habitat and stream quality because obviously they're toast. Cities are all more than 10 to 12% paved, and there's no reason to spend any more money in them in terms of salmon habitat and water quality because you'll never get above this threshold for getting high quality BIBI. The logical flaw in that argument that I want to point out is that they're talking about a statistical relationship that's based on conventional development, conventional parking lots, conventional roads, conventional buildings. If you change the way that parking lots work, this is a new parking lot. It's so satisfying to be able to go on Google Earth and see the projects that you worked on actually happen. This is a new parking lot at a mall, one of the nation's first suburban malls outside Seattle, the Northgate Mall, that shows bioswales in place in the parking lot that change the hydrologic performance of that parking lot and change the water quality of the water coming off that parking lot by filtering water that drips the benzene and PAHs, polycyclic aromatic hydrocarbons that come off of cars and leaving them in this filter zone instead of sending them directly to streams that have salmon in them or had salmon in them. So if we did development in an unconventional way where everything, roads, buildings, and parking lots, essentially comes with its own kidneys and filters itself, we wouldn't see, I would say, we will not see that relationship between percent total impervious and the benthic index of biotic integrity. That's my hypothesis. I think it's going to be true. And the data seem to show that these areas are working so far. I'll show you an example in a second. What we did was we looked at, when I was working in Seattle, we looked at single-family homes to try to figure out how much detention they could do. How much work could the private residential parcel do in the urban water system if you decentralized the storage of stormwater to protect streams from being flushed out by big storms? And it was amazing. In a watershed about 11 square miles, an urban watershed, we figured by looking at actual designs for typical 5,000 square foot lots, not by pretending, but by actually looking at people's gardens and yards, what we could do, and we figured that we could store upwards of 1,800 acre feet of water in that 11 square mile watershed, a lot more than it stores now. We also figured that the right-of-way, the roads, and the sidewalks around them could store a lot more than what they store now. Multifamily, not much tougher, and parking, probably the main thing is to do water quality improvement rather than detention. But it's amazing how much more water we could store if people had cisterns for their roof, rain barrels, cisterns under their decks, just simply what we call sometimes recessing a lawn, where you dig down an area of the lawn or you build up a berm on the side of the lawn and you end up with a storage area for rainwater in the wintertime. There are a lot of things that can be done, many of which don't affect use and in fact could be interesting for seeing different plants grow seasonally in the garden. This is an image that shows the way that streets and street drainage connects directly to streams in the Northwest. This is a very typical system in much of the country, where the public drainage system that's constructed, in this case ditches, drains directly to streams. It's that connectivity, the ditch as an easy flow direction for water, or the pipe as an easy flow direction for water, during which very little filtration occurs and very little storage occurs, that causes the streams to be degraded. Many aspects of degradation are caused by that deterministic variable. One of the things that people have been trying to do, and this is a project I'm kind of cartooning here that's actually under construction now in Seattle, is to take pipes and what's called daylight them, to make pipes that have stream water in them or have channelized groundwater in many cases, make that water visible as a constant flow to the public in a park and make it available as habitat. This is a kind of crazy but strategy that they actually have been building, where they insert a weir into the pipe and then a lateral arm, and the weir causes the water in the pipe to backwater. It causes it to pond behind the weir. And when the water ponds, it drops the sediment load that it's carrying because it has no energy to suspend that water, that sediment. And the sediment is one of the biggest problems in the stream. So what they do is now they're planning to hydraulically dredge this big 6-foot diameter pipe to remove that sediment and keep it out of the lower stream system where there are salmon. So they're using it as a filtration opportunity, and by creating this ponded water, this pipe is quite deep in the ground. They dug a kind of a valley here to reveal it. You have to imagine the earth covering this pipe, but being open in this channel area. The water is essentially siphoned off by a lateral pipe, and it moves through a park space that looks like this, something like this. where you don't see the pipe at all, but new senior housing has gone in, a grocery store, movie theaters, a whole bunch of things have gone in, and they used the buildings to take up the change in elevation from the street level to the level the pipe was at. So the buildings allow you to make the deeper valley without seeing steep sides and a kind of a cavernous feeling. And then when you're in there, you see a stream that actually is the base flow revealed from this pipe. Storm flow goes right out through over the weir. So when the big storm comes, and it could be an order of magnitude difference or 2 orders of magnitude difference, could be instead of 5 cubic feet per second, 500 cubic feet per second of stormwater flow, it goes over the weir. So you retain the value of that pipe as a stormwater pipe in extreme events, but you don't hide the base flow. This is a David Macaulay drawing of a street as if you could peel away the asphalt and see underneath the street. This is a typical urban street, all the crowded stuff under it, all the utility ducts, sewer, storm sewer, sanitary sewer, water supply pipes, electrical boxes. There's a lot going on underneath there. Luckily, David Macaulay is there to help us understand it. This is my version. This is a little bit more boring, but it's a GIS map of actual pipes. And it shows lateral pipes. This is a storm sewer system and a sanitary system. It's a combined area of the city of Seattle where houses drain to side sewers. Side sewers go to laterals, and laterals go to mains. The whole strategy for changing the way that urban water works, the drainage water in particular, the rainwater, is to essentially add a green skin to this, to make the city function less like an umbrella where all the water is shed and more like a sponge where water is detained for some period of time, if not permanently, by infiltrating the groundwater. What that would look like if we used the private property strategy is this. You would essentially add mulch to everyone's yard, add cisterns to everyone's roof or deck or garden, and you would get a green skin on the private parcel. The other strategy, which for many people is much easier in the municipal side, is to do it in the right-of-way, the street, sidewalk, and sort of planting strip zone, which is already owned by the public, and by area in a city like Seattle or other grid cities makes up as much as 38% of the city by area. It's a lot of land, and it has the dirtiest water coming off of it. So if water quality is your main concern, then you really want to treat the right-of-way, put the green sponge in the right-of-way. If water volume is your concern, both the right-of-way and the private parcel matter, but maybe the private parcel matters actually more. It's harder to get private people to line up along something like this and get them all to do it than it is to do it in the public right-of-way if you create new standards for construction and maintenance. So that's often why people choose the public right-of-way. This is an example in Seattle of a public right-of-way that's been altered. It's what it used to look like, a street with a relatively low density of 4,000 to 6,000 square foot lots, and informal drainage of a ditch along the sides, no sidewalks, lots of crazy parking. People didn't like it. They felt they'd been promised better. The city hadn't delivered, so they were agitating. The city delivered something which is a very new thing for Seattle and the rest of the country. It was a C Street, and what it does is it uses little bowls along the street to hold water off the street, which are connected by short lengths of pipe. There's only one sidewalk set off to the side, but 2 wide strips are painted of white paint on the street. And people tend to actually walk on those rather than walk on the sidewalk, because the other thing they did was to curve it in ways that urban designers find makes their skin crawl, but looks more suburban than many of us would like to look in an urban area, but it actually calms traffic, and the narrowness of the paved area, it's about 18 feet wide, 2-way traffic, makes you really think and slow down. And parking is often little pods on the side where people share a mailbox structure, but go to their private homes. That's what it looks like when it was first built in a perspective view, the before and the after. The other advantage of this, the reason why this was a win-win design, is that it was cheaper than putting in 2 sidewalks and 2 sides of pipe. What it costs in Seattle, because of a bunch of things related to family wages and inspection requirements, is about $1 million a block to put in formal drainage with pipes and catch basins and sidewalks on both sides. The C Street cost $750,000 per block, so it actually is a savings in their context. And it would be in many places where people are trying to make a difference. This is the performance of that system. Before it was constructed in 2000, the rainfall that year was about 8 inches of rain, the runoff volume about 5,000 cubic feet, and 625 cubic feet per second was the runoff rate for storms. After it was built, there was a big rain year of 9 inches, 132 cubic feet of total runoff, a big change. That would be 97% reduction, and 15 cubic feet per second as a runoff rate. So the monitoring data showed as a big success, and now the engineers like it, and it's been built on more than 20 blocks in that district of the city. This is what it looks like in an area where they did a different, more formal, urban-looking version at a higher density in a neighborhood that was completely restructured as part of Hope 6 funding programs. And this actually uses soil underneath the planting strip as the storage place instead of using a kind of garden-like or naturalistic set of berms and bowls to store rainwater. It stores it in an engineered soil that has a certain amount of void space and can detain a lot of water. And they modeled it, and now they're measuring to show the difference in the flashiness of the streams where that water would drain off of the development into those streams. Now we see a much lower peak in the hydrograph showing a big change in performance. This is a modeling result. Now they're actually monitoring getting the data for the real performance. And there are different versions of this. On a steeper street, they do a version now that's more of a step pool structure. And in little residential areas where they can't afford to do much, they do a strategy that costs $15,000 per little kidney, where the water just comes down to this kidney and is somewhat cleaned and detained and then runs out the other side. So it's just an addition to the existing stormwater system. It's not a replacement, but it creates different detention and quality benefits. So I want to talk about coastal areas for a couple of minutes now and move on to climate change. This is coastal sprawl. For reasons I don't have time to go into, we have a hard time controlling sprawl, and we can expect that coastal sprawl will continue. That's one big reason why urban biodiversity and urban design can't be taken out of the regional biodiversity picture. If coasts are going to become urban, most of our coasts are going to become urban, then we have to make sure there's a structure in place and attention to processes that allow species to move from the marine edge along rivers to lakes and wetlands in the inland. We have to. Otherwise, we'll cut off the marine world from the terrestrial world, and that will reduce the number of species dramatically. So we have to do something in a suburban and as well as an older city, central city matrix to be able to make this work. One of the big concerns people have on the West Coast and the East Coast, and really all over the world, is submerged aquatic vegetation. This is the new, discovery. It's not really a discovery, but it's becoming the poster child for coastal issues. It's a submerged wetland that's below low tide. It's not the wetlands you think of exposed at low tide on coastal areas. It's the ones you don't see. So it has plants like eelgrass and a whole bunch of other species that are typical of Chesapeake Bay, typical of the marine areas around Boston, typical of the Puget Sound and the Gulf of Mexico. This is the hypothetical maximum distribution of these submerged aquatic vegetation through Chesapeake Bay. It basically lined, it's a little bit hard to see in this photograph, but it basically lined the edge of all of these coastal areas and around islands in a kind of a halo. And the importance of that is that this connectivity, like the network connectivity I talked about in Seattle, where you have to pay attention to the whole way that the water flow occurs from the roof or the parking lot all the way through to the coast. The importance here is that marine species, crabs, birds, marine-related birds, fish, use this area as a kind of nursery. Female blue crabs molt and then take refuge in this submerged aquatic vegetation. You find more juvenile blue crabs in that vegetation than any place else. And we're learning more about larval dispersal for all kinds of crustaceans and for other animals. And that's very important to the larval dispersal and to the development of juvenile fish, where they go to these shallow areas basically to hide in the weeds from the big fish that are trying to eat them. So it's very important to the survival of juvenile salmon in Puget Sound and very important to the survival of other fish here on the East Coast. The blue crab is one, obviously, that matters quite a bit. And the mummichog is another one that's an important trophic chain, an important food source for larger fish, but needs to survive long enough in the SAV beds to make it out there to be that part of the food chain. And then amphipod species, which are very small, live in the grasses, and are an important food source for fish like juvenile salmon. One of the things that I haven't been able to get anybody to build yet, this is an unbuilt, this is a to-do item for me, is to build submerged floating beds for these submerged aquatic vegetation species. And I think that we could do that in urban areas by using basically pilings and then cabling these floating buoyant beds at different depths in the water, depending on the clarity of the water. For example, light penetration is one of the big limiting factors for the growth of these species. So if we need to raise it in a turbid urban water area, then we need to raise it. So we would just set it at a higher elevation in the water column where they get more light. But it's a critical kind of skirt to think about, and this relates to sea level rise and climate change, I'll talk about in just a minute. And this is what it might look like to go through one of these areas on a kayak, where there are these, some floating, some submerged, different kinds of habitats on the edge of a city. This one is actually modules on the land connected to modules on the water that could be somewhat built by volunteers. I don't know how that would actually work, but it could happen. It's important in some cities like Baltimore to pitch the volunteer piece of all these things. That was Baltimore. In Stockholm, I want to make a point using a development that's occurred there and their planning approach to this coastal issue. It's also a matter of nested scales all working together. This is a development that's done a great job of doing what the Europeans do best, which is thinking of a city as a metabolism, as having a metabolism. There's energy, there's waste, there are cycles. How do you keep it all real tight? Don't waste any energy, reuse all your waste, material waste, and energy waste. And they've been doing a great job of that. I won't go into the background of it much, but this is called the Hammarby Sjöstad district of Stockholm. It's a new one built on a brownfield site. So it's got all the great earmarks of design we try to do now in cities. It's a district of 25,000 inhabitants. It's a big chunk of Stockholm. It's a kind of a new city center down to the south. And they use some really beautiful, simple elements to do their stormwater conveyance in what's a very modern architectural setting. And they end up at the water's edge by creating these wetlands that sustain a lot of species along the edge there of the city of Stockholm, connected to the Baltic Sea. They also have, this is the fun thing I think, these land bridges that go across to a larger regional park and connect species to the ocean. What I would give to see an American city build land bridges like that, or even just tunnels, but especially land bridges, for species to be able to get to water. This is the stormwater park, which functions as a corridor to bring animals to the water's edge. But the two are important also because of the redundancy factor there. If one of them, for some reason, is not good to use, maybe a predator is sitting right here, a coyote, the other one might be available. So it's important to have more than one of these things. And it ties in to this larger regional plan that they call the Green Wedge Plan in Stockholm, of parks that they've created for biodiversity and recreation. So that whole system is somewhere right in here, in the center of Stockholm. There it is. The Hammarby Sjöstad is down here, I think, and this is the National Urban Park. So at different scales, they've actually created different ways of preserving biodiversity. At the city scale, at the regional scale with the green wedges, and within the city at the district scale. That's what needs to happen. We have to nest these strategies one within the other, like these Russian dolls that we see, folk art. This is an oak, which is an important species to the Swedes for cultural reasons. You can see why. Oaks get to be one of their largest diameters in the world in Northern Europe. This is a 47-foot circumference oak, maybe 800 to 1,000 years old, and these are the kinds of trees they want to preserve, and you can understand why they would want to do that. This bird actually is critical. They call it a mobile link. It plays a role in planting acorns and actually in collecting acorns, and it's the Eurasian jay. And studies in Stockholm have actually put a dollar value on that activity. If people had to get paid to do that job, what would it cost to replace a nesting pair of jays? And they're estimating it at somewhere between $5,000 and $22,000 per nesting pair, depending on if you're just seeding a certain way, very simply like broadcast seeding of acorns, or if you're actually planting. So that's helpful, I think, to consider the dollar value of ecosystem services. It's not a new idea, but it's one that relates directly to biodiversity in this case. Ports. Ports are a hot area for thinking about biodiversity, especially in Europe, because the European Union has put out a new directive for biodiversity. I'm going to talk for a minute about Antwerp here in Belgium, and later I'll mention Rotterdam. So you can see them there. They're very important ports right now in Europe, two of the larger ports in the world. This is Antwerp in Belgium, the harbor area. This is the natterjack toad, and the natterjack toad is a common species to primary successional landscapes and shoreline areas of Western Europe. What they're doing is an interesting strategy. They're saying there are certain key patches that will be left for the toad, and the idea is that where the toads can travel back and forth from permanent patches to find temporary patches of vacant land as the port manages its tenants over time. That's an important idea. They're calling it a habitat backbone scheme. And the point I want to make with this is that there is a shifting mosaic in urban land. The uses of land turn over pretty quickly relative to other areas. And it's important to be able to find a way to have a source area for a species. At the same time, we provide what they're calling here, I think, search zones, this bricked pattern, where the toads can travel to find a suitable habitat in the larger area as it becomes available and then move as it goes away. So the idea is to create some kind of source area, they call it the backbone, and then be able to move through a shifting mosaic to locate other suitable habitat. This is an example of a series of cargo ships at a port like Antwerp, and I keep thinking about how can I persuade people to build this SAV strip. So this is my SAV strip, and of course there's a problem in an active port area with big draft, deep draft cargo ships. You'd kind of have to do a reverse drawbridge on this. I know it's a problem, but I'm thinking about it. I'm not going to give up, and probably drop that down so the ships can get in and out. I don't know, maybe at night you pull it back up and you've got a night shift for the animals to move and a day shift for the boats to move. I think it's solvable. I'm talking to some Dutch engineers. I think they can help me. So climate change, and then I'll wrap up. Precipitation. I'm not going to show a lot of data slides for this because I think we all hear about this quite a bit. At least people who are paying attention hear about this quite a bit. Although, until January '09, we basically lived in the American media bubble where we heard very little about this and the rest of the world was hearing a lot about this. So happy with the change. This is a slide that shows the predictions for changes in rainfall in North America. And the red zones are areas that are expected to get a more intense rainfall less frequently. So what we call statistically the 20-year storm is going to be described in the future, the models say, as the 4 to 6 year storm. So we'll see a very big storm more often in terms of years, but less often during the year. We won't get storms for a while, and then we'll get really big storms. That's the prediction, both for North America and for Europe. Then there are other areas that will get less intense rain and probably less rain overall. We're seeing already the effects on vegetation of what people believe now is climate change with, for example, the sudden oak death in the West Coast, Washington and California, or Oregon and California in particular, on some species where they're sensitive to drought in the fine root system, and then the die-off of pines, in particular in the Southwest. So we're already seeing, this is a drought issue that connects to an insect infestation. When the trees are weakened by drought, then the insect comes in to finish them off. These large patches of dead trees will change the ecosystem and the configuration of patches and corridors and source areas in the Southwest. They're already changing it, like the Yosemite fires did, but on a much broader scale. In addition to the vegetation changes that we're already seeing on the West Coast, we're, of course, observing data about sea level rise. I don't know if anybody saw the article that came out just, I think it was last week. There was a Copenhagen summit. People were talking about sea level rise. It suddenly made it into the Washington Post. I want you to know that I am writing to the Ombudsman every week at the Washington Post, trying to find out why it is not a headline. Because Washington is so vulnerable to a change in sea level rise that could be as much as a meter within this century. I can't for the life of me figure out why it's not on the front page. It's buried in the science section, which, as you know, most people do not read. These data show sea level increasing at a faster rate than the IPCC models, the Intergovernmental Panel on Climate Change. And that is very significant. We're also wondering what's going to happen with hurricanes, but of course the data show, or the models suggest that hurricanes may actually decrease in some parts of the world, like here, in intensity, and increase here, but we don't know. This is a historical map of past hurricanes. The jury's out, and that's a really big subject. This is a big uncertainty to not know whether hurricanes are going to increase or decrease or stay the same. And the reason for that is, let me give you a little bit of a sense of the way that the city of Rotterdam is approaching climate change. They've done a plan called Rotterdam Climate Proof. And they've said that their main challenges are the increased intensity of precipitation with longer summer droughts, those are I was just talking about with that other map, a rise in sea level, and they were talking about 2 to 3 feet by 2100. I think now we're talking very clearly about 3 feet. At least many people are in trying to think about what we need to be prepared for. And then increased river flows from rainfall that happens way inland in the former Czechoslovakia and in eastern Germany and comes down the river to Rotterdam. And then groundwater rising with an increasing water table in general, with an increasing amount of water at those storms. So they're trying to figure out how to design a city for that. They've been doing a lot of work on floating houses in the Rotterdam harbor. And pretty convincingly have shown that that can be a useful strategy. They've also done a barrier. This is a classically Dutch and now European strategy, which many Americans have not even heard about. This is the Rotterdam barrier, and it sits in this open position most of the time, and when a storm is coming, it closes. Just rotates on big hydraulic spools, and when it comes together in the middle, it drops down. It's a shallow river mouth, so it's possible to block it with a fairly low barrier. That's what it looks like, too, when it's closed. This was built, completed in '97. It was first actually used for a storm in 2007, and it worked. Imagine an American politician who persuaded people to pay tax dollars to build something that didn't need to be used for 10 years. That person's out of office by the time that the thing actually becomes useful, but this is the context we're working in. It took 10 years to build it. And then it wasn't needed for 10 years, but clearly they're ready, and we are not. London, this is the city of London, their biodiversity plan was finished in 2002, has taken the climate change approach of focusing on corridors and connectivity. This network connectivity thing is essentially their climate change strategy. They're thinking species are going to want to disperse, they're going to try to find better locations, they're going to go up in elevation, they're going to go north in latitude. Within cities, we're going to have to provide for this dispersal, and also outside cities. There's a new field of ecology called road ecology, which is focusing on that. The ecoducts or land bridges I showed you are part of that whole approach to thinking about dispersal as the way that species will shift and adjust to climate change, just as they did when the glaciers came and the glaciers went away. Species moved south when the glaciers came south, and they moved north when the glaciers went away. Species are going to move north when it gets colder, when it gets hotter, who need colder environments, and then stay there. I can't say that I think climate change is going to reverse like the glaciers. It may be on a very long cycle. The length of the Pleistocene, we'll see some change. This is a map done by some faculty at University of Arizona who are trying to show with relatively coarse topographic data what would happen with a 1 meter increase in sea level to the East Coast. This is the map I want to see on the cover of the Washington Post, because here's D.C., and the red area goes right up into D.C. and the Potomac and the Anacostia. Of course, it's going to affect much of New York City, much of New Jersey, and it's not just the land, it's the water supply of these places, where salt water would rise into what's currently a freshwater zone, and cause saltwater intrusions in these zones. So it's water supply, it's downtown flooding. If pipes that currently discharge stormwater to the ocean don't have tide gates in them, then ocean water comes up those pipes at a big storm surge event and can flood the downtown. That happened to Baltimore in Hurricane Isabel in '93. These are very serious concerns, and in the Chesapeake Bay area, we're already subsiding almost as fast as New Orleans. Chesapeake Bay is the second fastest subsiding region of the United States. You can see by these leftover vacation homes that it's had consequences, and it's been rapid. It's been going at quite a pace. These are not old structures, but the people who own them, this is the catch of it all, not only did they lose their investment in a vacation home, which might have provided a real estate nest egg for future generations or for their retirement, they actually have to pay to remove the structure because they're now in the coastal zone, and they're not supposed to be. So the questions about how we, from areas like this, as sea level rises, just in terms of property, ownership rights are very significant. Probably we'll use transfers of development rights if we're smart to relocate people before the crisis happens. But when I talk to my Dutch engineering friends now, fairly often we're working in New Orleans, and I asked them one time, what is it Americans are good at in engineering the coast? And they said, they thought for a second, there was a long silence, they said, evacuation. So actually, they're studying the way we evacuate cities like Houston or New Orleans because they don't evacuate. They have a social contract where they deal with the government in a way that says, you're going to be protecting us. We are not going to have to evacuate. But they are changing their perspective to say, okay, with sea level rise, maybe we won't be able to always give you a 1 in 10,000 risk of flooding. That might be a risk of loss of life. So you Dutch people, you need to learn to evacuate like the Americans, just in case. So they're looking at how we evacuate and learning from us. I think, unfortunately, that's just about our only strategy at this point, though. So we have to be real good at it, real good, and think about what the implications are. Here's a city that would be very difficult to evacuate. Has, to my knowledge, never been evacuated, not since the British invasions, anyway. And this is a map that shows Manhattan, the Bronx, Brooklyn, and Staten Island, the boroughs of New York City. And the blue areas are what would be inundated if a hurricane, a Category 3, hits New York. The last time a Category 3 hit New York was 1938. I'm sure some people here have family or may remember what the consequences of that hurricane were. 700 people died, mostly in New England, because it went over Long Island and into Rhode Island and into New England. And structures were just obliterated along the shoreline. This is a wall of water about 35 feet high, moving 60 miles an hour when it hit land. Picture that. So there's a storm surge of 22 feet, and on top of that are waves. If this storm, it went over, as I said, Long Island, in the middle of Long Island, if this hits New York City, this is now, besides Miami, this is the most vulnerable city from an insurance perspective in all of the United States, because the value of the buildings and the property is so high, and the likelihood of a hurricane is pretty high. No one thinks about it. They just get 6 inches of rain in New York City and everyone freaks out because the subway floods. What would happen if they had 22 feet of storm surge? JFK is underwater. Much of lower Manhattan is underwater. The whole area here in Brooklyn, full of rather poor people, mostly from the Caribbean, is underwater. There's a lot of risk here for people, and if you add sea level to that, then the areas that we've been inundated go much higher. So there are proposals on the table by engineers, including my Dutch friends, to put storm surge barriers in place in 4 places around New York City. Here at a bridge crossing, I think that's the Whitestone, and here at a crossing from Floyd Bennett Field to Rockaway Beach, here at a bridge, and here at a bridge from Staten Island over to New Jersey. If they build those 4 barriers like the Rotterdam barrier, we may be able to actually address some of the storm surge issues in that coastal area. And what I have, this is a very quick illustration, but I'm out there and I'm trying to get those engineers to think about, okay, if you build these barriers and you cut off the salt water from the fresh water, what are we going to do about these submerged aquatic vegetation beds? I'm soon going to get a tattoo of this, submerged aquatic vegetation. I show up in a meeting and everybody starts saying, oh no, here we go, submerged aquatic vegetation. But if we lose this system that we currently have fragments of along the coast because of sea level rise or because of the construction of hardened dikes and barriers of various kinds, we will lose our fisheries. We'll lose a $4 billion food industry that's a great source of healthy food. So I don't think we can afford it. It's not just biodiversity, it's human health, it's a way of life, it's an important food supply. So I think I'm stopping there. Thank you. Thanks for putting up with that.